Okay, this is the reflection and refraction experiment. We're going to start out here with just some real basic theory. What you see on the board here is a gigantic piece of glass. You see that vertical line down the middle that kind of cuts the screen in two. On the right, you have just solid glass, and on the left, you have air. All right. So we're going to represent light as traveling in these straight lines that are called rays. That's the ray treatment of light. On the left, you have this ray of light that comes from some light source. That's the pink line there, or the red line. So it comes from some light source and it's traveling through air and it hits this piece of glass. So what it does not do is it doesn't go into the glass in a straight line path. When it goes into the glass, its path actually changes. It bends a little bit. So hopefully you can see there that the angle is changed. Okay, so that's what refraction is. That's the bending of light when it comes into glass. So we're measuring a couple of angles here. There's a big horizontal dashed line there. That's the normal. That's what's called the normal. It's just an imaginary line. It's just a theoretical line. It doesn't represent anything real. So that's the normal, and we're going to measure angles from the normal. So there on the left, you see theta sub A. So that's just the angle in air that the glass, or that the light makes when it hits the glass. Now then on the right, you see theta sub G. That's the angle between the normal and the ray of light that's inside the glass, all right, traveling inside the glass. So those two angles are not equal. So there's a relationship called Snell's law, and that's what you see circled there. The NA sine theta A equals NG sine theta G. There's a quantity called the index of refraction. That's what the N stands for. Every substance has, that light can travel through anyway, has an index of refraction, okay? And for air, it happens to be approximately 1. So we're going to just say index of refraction of air is 1. In reality, it's like 1.000 some other decimal places, but close enough to 1, we just say 1. A vacuum would actually be perfectly 1. So then the index of refraction of glass is the NG, and that's one of the quantities we're going to be finding experimentally in this experiment. You're going to do this and make measurements of angles with protractors and calculate what the index of refraction of the glass is. Okay, now if you'll take a look again, understandably your eyes might have wandered a bit because there wasn't anything changing that picture, but now if you'll take a look again, there on the left I've added something. So you see right there where it says air up on top, there's another ray of light now, all right? So this is reflection, okay? So a ray of light that originates from air, they're in air, they're on the bottom and strikes this piece of glass. It bounces off and reflects, so that's what reflection is. And we can make an angle, we can measure an angle too between the reflected ray and the original ray, or what's called the incident ray, okay? That angle is going to be the same, all right? In other words, the theta there on top is going to be equal to theta A, okay? So you always have both of these going on at the same time, or well, you usually have both going on at the same time. So if you have an incident ray, then some of it gets refracted into the glass and some of it reflects off of the glass. We're not going to worry about how much of each, but some you have both processes going on at the same time, okay? So you've got reflection there on the left and refraction there on the right, okay? Okay, so now let's talk about how we do this for real with equipment. So here, right here, is an inexpensive laser like you can buy at Home Depot or somewhere like that. So you're going to use a laser that looks like this. A couple of you might have one that looks a little slightly different, but anyway, something like this. So we'll get a laser light out of that. And then your piece of glass is going to look something like this, a glass prism, okay, or glass triangle. So something like this. So what I've got on the board right now is a diagram of what's going to happen to a ray of light, some of what's going to happen anyway, as it enters a piece of glass, as it enters a glass prism. So if you look there on the left, that would be where the ray of light originates, from a laser source. And so it strikes the left side of this glass prism, travels through the glass, it gets refracted into the glass. Then it comes out the other side on the right and it gets refracted again. The angle changes again. So that's essentially the kind of measurement, the kind of diagram you're going to come up with for refraction. Okay, that's the refraction part of it, and you can draw these normals and measure angles and so on. Okay, so that's the kind of thing we'll do. Okay, now if you'll take a look again, slight change now. I've erased the line that's actually represents the light traveling inside the glass. Okay, now it still would actually do that, but the thing is, you're not going to see it though. There is light that travels through the glass the way I had it drawn previously, but once it gets inside the glass, it doesn't come out the top of the glass very well, and so you probably won't actually see it. Some of you might, if you're lucky, you might see it kind of faintly, but most of the time you don't actually see it. You can pretty easily see the ray that enters on the left and exits on the right. So, and you can, run that all the way up to the surface of the glass, and then you just have to construct the line that represents the ray of light actually traveling through the glass. Okay, so this is more like what you'll actually see. Okay, now take a look again, and I've added something else. There on the left, the incident ray that first approaches the glass, I've drawn it just extending across the top of the glass. And that's probably the way it'll actually look when you do this for real. The laser that we're using, the light comes out in sort of like a big vertical sheet. And so some of it is going to go into the glass, but a lot of it will just kind of bleed across the top of the glass, and you'll see that. And you might mistakenly think that that's the refracted ray in the glass, but it isn't, okay? So that's something you want to watch out for. In other words, what you're looking at right now is closer to what it's really going to look like, okay? And that ray of light that looks like it's inside the glass on this drawing, that's actually just on top of the glass, and it's not being refracted. It's just some of the original light that first approached the glass and just extends over the top of it. When you're doing this for real, you'll want to ignore that. That's not really of any interest to us. And the ray of light that actually is transmitted through the glass, that refracts through the glass, you probably won't see that. You'll just have to construct it yourself, okay? So this is more like what it'll actually look like. This, if you look again, is more like what we really want to construct, okay? So that point may be a little confusing. You'll have to be careful about that. Now if you'll take a look again, we've added a couple of other things. Now we're going to look at reflections as well, because in addition to the refraction we've been talking about, you also have reflections going on. So you're going to be doing a separate drawing just for reflections. So you'll notice I've added a couple of reflected rays. There's one of them. So that one's in the air, just reflecting off of the glass. But there's also a reflection that's going on inside the glass. You have the original, well, I shouldn't say original, but the ray of light that's inside the glass, it's going to hit the surface of the air and actually reflect off like this, okay? So you get a reflection inside the glass. It reflects off the air. That may seem a little counterintuitive to you. You might not have thought that that could ever happen, but yes, it happens. You can actually reflect off of air. So we're looking at two reflections there, and when you get to that diagram, it gets a little harder to actually make a diagram. And getting the rays where you can get the reflection inside the glass is especially a little more difficult. It gets harder to do it very accurately, but it's not anything you can't do, okay? Okay, now let me show you what this will look like equipment-wise. There's a big round plate with a piece of paper and a prism sitting on top of it. There's the laser over there. So there's a protractor. So you're going to be tracing out things on the paper and measuring angles in order to make these calculations. Notice there on the left, the laser, on the back edge of it, there's some cards there. Okay, you see some cards. It works better if you prop up the back of the laser a little bit so that it aims more down toward the paper. It's just some trial and error. You just kind of try stuff and see what actually works. Okay, and same way with orienting the prism itself. So let's turn out the lights and then I'll show you what this actually looks like. Hopefully you can see with the laser turned on. There you see, there's the laser turned on, the incident light coming in and coming out the other side. And if you notice real carefully, notice you'll see a faint red line across the top of the prism. That's just part of the original incident light bleeding across the top of the prism. We don't want that. But the ray of light that's really transmitted inside the glass from one side to another inside, you're not really seeing that. You just have to construct that from drawing, okay? So that's the deal. Be sure that you use a pencil on this. I really would not recommend using an ink pen. Okay, and one other thing. Now if you'll look again, I've changed this to where now you're seeing a reflected ray coming off of the side of the prism as well. I did that by just kind of orienting things a little differently. So anyway, just to show you what that looks like. Okay, I'll leave you to it.